Welcome back. This video will cover weight and balance in more depth as requested by one of you. Thanks, Jose. Weight in weight and balance is pretty simple. The more weight in the airplane, the more lift we need to counteract the weight. If we have too much weight, we won't have enough lift. And the airplane is able to fly over weight, but remember those limitations of positive and negative G's in the POH. These will be exceeded in turns, in turbulence, and when you overstress the airplane. Balance in weight and balance refers to the center of gravity location, and that's a point where the airplane would balance if suspended. It's also the point the airplane rotates around when you pitch, roll, or yaw. The center of gravity is usually located slightly forward of the center of lift. And that makes sense because it causes a slight nose-down tendency, and that helps at slow flights and high angles of attack. And during a stall, the airplane naturally wants to recover. Now, as far as the legality of doing a weight and balance calculation, there's nothing that says you must do one. But in FAR 91.9 it says, no person may operate a civil aircraft without complying with the operating limitations specified in the approved airplane or rotorcraft flight manual. And if you haven't done the math, how do you know you're within the operating limitations? Now let's talk about the fundamentals of weight and balance. If you've ever had to take a wheel off of a car, you know that it takes some muscles to unscrew those lug nuts. And sometimes you might need a breaker bar or something to extend the wrench. That's because the longer your lever, the more force you can get with the same amount of pressure. That's the basics of a lever. A lever usually has a pivot point or a fulcrum, and then a force pushing down. The way we measure force is by taking the mass of the object times the arm, or the length from the fulcrum to the center of gravity of our object. The length is measured in inches, and the weight is in pounds. So 100 pounds times 50 inches, that's 5,000 pound-inches. To go back to our wheel example, if you had a 12-inch wrench, you would need 3 times more force than if you had a wrench plus some sort of an extension of 36 inches. So the longer the arm, the less force required to do the work. And that's why our airplane tail is way far in the back. If it was right behind the cabin, it would have to be massive to have the same effect. All weight and balance problems can be solved with 3 basic steps. Weight times arm equals moment, and you do this for all the items. Step 2, you add all the weights, and then add all the moments. And finally, step 3, you take the sum of the moments and you divide it by the sum of the weights. And that's how you get your center of gravity. Let's look at a simple weight and balance problem. This is our plank and our weights. Let's put our 100-pound weight at 50 inches left of the datum. And the datum is the reference line where we measure all our distances from. We'll put a 200-pound weight 25 inches to the right of the datum. Now for our 3 easy steps. So we have 100 times negative 50 equals negative 5,000. Negative 50 because arms to the left of the datum are negative and positive when they're on the right side. For the second weight, we have 200 times 25 equals 5,000. So now for step 2, if we add all the weights, that's 300 pounds. If we add all the moments, we get 0. There's no extra moment anywhere, so we're balanced. That's simple, right? Let's take this a step further. Sometimes the reference datum, where we measure distances from, might not be in the middle. Where is the balance point? We still have the same 3 easy steps. If we take the weight of A times 50, that gives us 5,000. Weight of B times 90, and that's 9,000. And then the weight of C times 150, that gives us 30,000. So if we add everything up, we have a weight of 400 and a total moment of 44,000 pound-inches. And this last step we haven't done yet, but if we take our moment, we divide it by our weight, that will give us our center of gravity or our balance point. And that means that our balance point is at 110 inches to the right of the datum. We can also check our answer by making the datum at the balance point. This will make the arm for A at minus 60 and minus 20 for B, and it will be plus 40 for C. So if we go ahead and we multiply everything out, we have minus 6,000, minus 2,000, and plus 8,000. So we're in balance, there's no extra moment left over anywhere. And once again, a moment is a force, so there's no force on one or the other side. On the written test, there will be a few questions that ask you how you should move a weight to be in balance. It's the same process, just with an extra step. In this example, how should the 500-pound weight be shifted to balance the plank? We'll go through our steps again. 500 times minus 15 is minus 7,500. For B, it's 250 times 20, that's 5,000. And then the one other thing we have to add in is the plank, because the plank is not centered like it has been in all our examples. We have to account for that extra weight on the right-hand side. So what we do is we do the plank weight of 200 times 15, and that gives us 3,000. So now if we add everything up, the weight is 950, and then the moment is plus 500. So it's not zero, it means we have 500 pound-inches more on the right-hand side than on the left. Remember, if it was negative, it would be on the left, positive is on the right. So now the question was asking, how should the 500-pound weight be shifted to balance the plank? And this is a simple enough problem where we can think about it logically. Since we're 500 over on the moment, all we have to do is go 500 under, so subtract 500, and to do that, all we have to do is move the weight 1 inch to the left. That would be 500 times 16, and it would be minus 8,000, so all of our moments will cancel out. The other way to do this, and my personal favorite, is actually to use a system of equations. Basically make the left side equal the right side, and then solve for x. Since we know we have to move the 500-pound weight, we'll set the left side to 500x. That'll be equal to 250 times 20 plus 200 times 15, which is the plank. So we have 500x equals 8,000, which makes x 16. So in other words, the 15-pound weight has to be 16 inches from the datum. We can also change the question and ask, how would we balance the plank if we had to move the 250-pound weight? And in that case, we'd have to move it 2 inches to the right. There's also a formula to determine how to move things, and we can rewrite it a bunch of different ways to solve for each one of these variables. Let's do one more plank example with this formula. Say we have these weights and this balance point. How should we move weight B to have our balance point be in the center or right at 50? And I know this is a little different, it's measured from the left, but let's say we had our center of gravity at 50. How do we do that? We can use this formula right here. To solve for distance B is shifted, we need to take the total weight, and that's A, B, and C, and that's going to be 500. And we need to multiply that by the change in center of gravity. So we want our center of gravity to move 22 to the left, so that's minus 22. And we divide all that by the weight shifted. And the weight that we'll be shifting is 200 pounds, which is the weight of B. When you run the math, that equals minus 55. So we take our item B and we move it 55 inches to the left. Let's see if this actually worked. We're going to go ahead and change our datum to right above the center of gravity. 100 times minus 50 is minus 5,000. 200 times minus 25 is minus 5,000 once again. And then C is 200 times 50, which is 10,000. And doing the simple math, we see that it equals 0, which means everything is in balance. This formula is actually really useful in the airplane. Let's say that you did your weight balance calculation and the center of gravity is too far aft, so you want to move a heavier person from the back seat to the front seat. You can see how many inches forward you will move based on what you're shifting. Calculate the weight and balance and determine if the center of gravity and the weight of the airplane are within limits. And then you have some numbers there. Let's first look at the figures to see what we're working with, and I'll give you a couple pointers on that. With this specific problem, on each one of the little table things for occupants and fuel and all that, you have the arm listed there as well. So if you have to do a calculation for like 37 pounds of baggage, you just take that times the arm and you get your moment. The other thing on this one is it says that oil is included in basic empty weight. The empty weight and the moment is given to you as well, kind of right in the middle. And if you do your calculation and it's off by a lot, that's probably why. So now back to our problem. Step 1 is weight times arm equals moment. We've got front seat occupants, they're 350 pounds. If we look at our chart, it doesn't go to 350, so we can do it two ways. You can take the moment for 200 and add that to the moment of 150, or you could just take 350 times the arm of 85. I'll be doing the multiply method, and you'll still end up with the same answer. So we'll take 350 times 85, and that's 29,750. And since our moments are divided by 100, that's 297.5. For the rear seat occupants, that's 325 times the arm of 121. That gives us 393.3. Now for baggage, we take 27 times 140, and that gives us 37.8. For our fuel, it's 35 gallons, and a standard weight for a gallon of fuel is 6 pounds. So we take 210 pounds times 75, and that gives us 157.5. As you can see, those numbers are really close to what they give us. They're just rounded a little bit. So now we go ahead and add our total weight, not forgetting the empty weight. And that's 2927. And then our moment is 2440.1. So we've done our 2 steps. Now the third step is to find the center of gravity, and for that we take our moment divided by the weight. So 2440 divided by 2927, that's 0.8336. It just means we have to multiply the answer by 100 because our moment was divided by 100. So our center of gravity is 83.4. So now let's look back at the question. The question says, calculate the weight and balance and determine if the CG and weight of the airplane are within limits. This is where our second chart comes in. Our weight was 2927. So if we look down 2927, it happens to fall in between 2920 and 2930. Now if you're a nerd like me, you can interpolate, and for 2927, we have to be between 2395.7 and 2480.6. If you're not a nerd, you can look and you can just see that 2440 happens to fall in between all the numbers that are there. So there we go. We're within weight and balance limitations. So once again, back to the question. We are within limits. We know that. Now the center of gravity that we calculated was 83.4. So the answer would be 83.4 and within limits. For this next question, it says, what effect does a 35-gallon fuel burn in the main tanks have on the weight and balance if the airplane weighed 2890 pounds and the moment over 100 was 2452 at takeoff? Since we're not moving anything around, we're simply subtracting the fuel, we can go ahead and just do that. The 35 gallons of fuel is 210 pounds. So our takeoff weight was 2890. We subtract 210 pounds, that's 2680. And then the moment, we can figure out what the moment is for 35 gallons of fuel based on the chart, and that's 158. So if we take our moment, 2452, and subtract our fuel moment of 158, that's 2294. So if we go ahead and look at that other chart, we look at 2680, and we have to be between 2123 and 2287, and our moment is 2294, which is too far aft. Looking at the answers, there's only one that can make sense, and that's the weight that was reduced by 210 pounds, and the CG is aft of the limits. Hopefully I'm not going too quick and this is all making sense. Here's another question. What is the maximum amount of baggage that may be loaded aboard the airplane for the center of gravity to remain within the moment envelope? This question is a little bit different in that we have a graph instead of a table, and that the moment is divided by 1,000 instead of 100 like in the last one. But the process is still the same, except in this example we don't have to multiply the weight times the arm, we just end up with a moment. For pilot and front passenger, we can follow our line up to 250. That gives us our moment over 1,000 of about 9.3, let's say. For the rear passengers, we'll go ahead and follow that line as well, and that's 29.3 at 400 pounds. Our fuel at 30 gallons has a nice little dot. We'll call that 8.7. We also need a weight for the oil, which is 8 quarts at 15 pounds. So we have 15 pounds for the weight there, and the moment's already given to us. One thing to be aware of is the scale on these charts. If you look at this load weight versus the load moment, you can see that it goes up by 10 on the left hand side, but on the bottom it goes by half, 0.5 for each line. So be careful when you look at all those. So now the total weight, if we add everything up, is 2195, and then the moment over 1000 is 98.6. Okay, so the question was, what is the maximum amount of baggage that may be loaded on the airplane? We can see on our center of gravity chart that the maximum weight is 2300. So if we do 2300 minus our total weight of 2195, we can see that we can only take 105 pounds of bags before maxing out the weight. So now let's see if that's within limits. If we follow the baggage up to 105 pounds, that's right at about 10. And so our center of gravity now is 108.6, and the weight is 2300 with those additional bags. Looking at our moment chart, we can see that at our max weight and at 108.6, we fall right inside the envelope. As you can see on this chart, there's a normal and a utility category area. And basically the difference is in a utility category, you're more restricted, but the airplane can withstand more G's or more loading. Let's look at one more example. Which action can adjust the airplane's weight to maximum gross weight and the center of gravity within limits for takeoff? We'll do the calculation again. The front passengers, 425 times 85, that's 361.3. The rear passengers, 300 times 121, that's 363. The fuel, 264 pounds times 75, that's 198. So our total weight, including the empty weight, is 3,004. And the moment is 2476. If we look at our charts, we can see that the maximum weight is 2950, so we are 54 pounds over the gross weight. The question was asking, how can you adjust the weight to maximum weight? And your options are to drain 9 or 12 gallons of fuel. And 9 gallons of fuel just so happens to be 54 pounds, which is the exact number that we're over the max weight. If we do a little bit of math, 54 pounds of main tank fuel times the arm of 75, we end up with 40.5 for the moment. Since we're not doing anything else besides draining fuel, we can subtract the moment from the old moment, and the new one is 2435.8, and the weight is now max weight 2950. And the moment falls between the forward and the aft CG limits. Why don't the other answers work? You can go ahead and run the numbers and see what you end up with, and you'll see that 9 gallons of fuel being drained is the best option. Now, just so you know, for practical purposes, if you load the airplane full of passengers, full of fuel, and full of the baggage capacity, you will be outside the CG, the weight, or both. So usually you need to sacrifice something. One thing I want to come back to is the little car lever example. If we look at our chart, we can see that things further back have a much higher effect on our moment or on our center of gravity location. For example, 120 pounds of baggage at arm 140 means a lot more for the center of gravity than a 120 pound front passenger. Let's look at some terms that we didn't cover during our examples. Standard empty weight is the airframe, the engines, and all operating equipment that's fixed in the airplane, and it also includes hydraulic fluid, unusable fluid, and full oil. So that's a standard empty weight. Basic empty weight is the standard empty weight, and that includes all the optional and special equipment that's installed. And when you're doing the weight and balance, you're using the basic empty weight. In the real airplane, you end up with a basic empty weight as well when your mechanics weigh the airplane, and that includes everything in the airplane. And just so you know, there is a standard equipment list in the weight and balance section of the POH that lists how much each thing weighs, like how much your autopilot weighs and what the arm is of that item. All that to say, when you get your basic empty weight, that includes the airplane and everything in it. Payload refers to anything that you could charge money if you were flying the flight for hire, so people, bags, and any sort of cargo. We've run into the arm quite a bit, but the arm is the horizontal distance from the reference datum to the center of gravity of whatever the item happens to be. A station is just another word for arm. In the airplane that I fly in, we have cargo loaded at a specific station, and that's just inches away from the datum. We know about the moment, that's weight times arm, and it's expressed in pound inches. The center of gravity is where the airplane would balance if it's suspended, and it's both lateral, vertical, and longitudinal. The datum, or the reference datum, is an imaginary vertical plane where everything is measured from, and it differs by manufacturer. In a Cessna, it's the engine firewall. In a Piper, in this example, the datum is 78.4 inches ahead of the wing leading edge, so that's good to know. And in a Cirrus, it's 100 inches forward of the cabin firewall. So they're all different, and usually they try to be in front of the airplane, so all the moments are positive. Maximum takeoff weight is self-explanatory. Maximum ramp weight, on the other hand, is kind of confusing. That's the taxi weight, or the total weight of the airplane plus the fuel that you expect to burn during taxi and engine run-up, and usually it's a little bit higher than your maximum takeoff weight. Maximum landing weight is pretty self-explanatory. Some airplanes you might see a maximum zero fuel weight. That's the maximum weight of the airplane minus the usable fuel. Some airplanes you might see mean aerodynamic chord as well, or MAC. That's usually used in larger airplanes, and jets especially, but you might see it in a POH like this 172 POH. The mean aerodynamic chord is the average distance from the leading edge to the trailing edge of the wing, and the center of gravity can be expressed as a percentage of that mean aerodynamic chord. We talked about the moment index, and that's the moment divided by either 10, 100, 1,000, and that just simplifies the math. Just remember to multiply back by that number to get your center of gravity. Standard weights are 6 pounds for a gallon of gas, 7.5 pounds for a gallon of oil, even though you buy it in quarts, so that makes no sense, and then water is 8.35 pounds per gallon. And finally, useful load, you might see that, and that's all the passengers, all the baggage, usable oil, and drainable fuel. In other words, it's the maximum gross weight minus the basic empty weight. Unusable fuel is fuel that you can't use, because that's the fuel that's left over maybe at the bottom of the fuel tank, maybe in the fuel lines, and it's not usable for propulsion. So that's all I have for you. I hope it was useful and helpful. If you have any more suggestions, please leave those in the comments below. I do need some video ideas. Once again, thanks Jose for the video suggestion. And until next time, have fun, fly safe, and always keep learning. See you next time.